Okay, good morning. Let's get started. So we were discussing about steady diffusion in non-orthogonal unstructured meshes, right? So we kind of formulated the diffusion part of the equation, right? So we will continue with that. That is basically steady diffusion equation on non-orthogonal unstructured meshes, right. So we have drawn a kind of a schematic for our notation for discretizing the equation, right. So that was we have a C0 cell and we have a C1 cell, we have this is your AF bar, and we happen to have a cell like this, right. So this is our C0 cell centroid, this is our C1 cell centroid, right, and then the line connecting them is along E xi, which is not parallel to AF bar, okay, and then we have E eta, and the angle between them is not 90 degrees, right. So that is what we have, and then we have of course also defined delta xi as this distance, and we said this would be our delta eta, right, the magnitude of the area vector, right. That is all we have defined, and then this is our phase f, okay. So that is what the schematic we had, and then we discretized the diffusion equation. The diffusion equation came out to be how much? The discretization basically gives you gamma grad phi dot f dot AF sigma on all the faces plus SC plus SP phi 0 times delta V 0 equals 0, right. So we said 0 cell is nothing but our P cell, which is the primary focus, and then we have 3 other neighbors, which are first cell, second cell and third cell, right. So we have 3 more cells there, fine. Then we formulated the value for the gamma grad phi f dot AF, right. So how much was that? Gamma grad phi dot f dot AF. This came out to be a long expression, right, in terms of partial phi partial xi as well as partial phi partial eta, right, and that if you help me write it out, this would be gamma f times how much? AF dot AF by AF dot E xi, right. That is what we have, times partial phi partial xi of f, right, and then we have what is the next term? Minus gamma f times we have again the same metric, that is AF times AF times E xi times E xi times E eta, right, times phi eta sub f, right. That is what we have. Essentially we noted that the diffusion flux, right, is not just phi xi, rather it is a combination of phi xi as well as phi eta, right. These are nothing but phi xi f is nothing but partial phi partial xi on f, and phi eta f is partial phi partial eta on the face f, right. So this is a combination of 2 of them, which is a consequence of what? Which is a consequence of up till now we never got the diffusion flux to be 2 components, right. It is always only one of them would survive. What is this a consequence of? This is a consequence of the non-orthogonality of the mesh, right. So as a result we have these 2 terms, which we would like to call it as a primary gradient, right, which is the first term. We would like to call this as a primary gradient, which is in the direction of xi, right, and then the other one we would like to call it as a secondary gradient, okay. This is everything that is not in the direction of xi, okay. So that is what we would like to term them as. Now let us see how do we calculate each of these terms. So what is the next step? Once we got the derivatives on the faces, what is the next step? Linear profile assumption, right. So as of now I would make a linear profile assumption only for evaluating partial phi partial xi, okay, only for the first term for the primary gradient. So, making a linear profile assumption, how do I write partial phi partial xi on the face f? So, we are talking about this face f. How do I calculate? So, we know what is phi 0, we know what is phi 1 because these are stored at the cell centroids. What is phi partial xi f? That is in this direction, right? That is in this E xi direction. How much will that be? Phi 1 minus phi 0 upon what is the distance? Delta xi. Okay. So, I can write this as phi 1 minus phi 0 upon delta xi for the face f. Okay. That is what we have. Now, this delta xi sub f needs to be there because delta xi would be different for different phases, right, depending on the cells we are connecting to. Okay. Now, let us not talk anything about the secondary gradient as of now, we would leave it as it is. I would like to write this entire thing of minus gamma f, this entire quantity as I would like to represent as some name, let us call it a secondary gradient sub f, okay, S g sub f, which is basically minus this entire thing, entire expression. Okay. Then what would be my, then what would be the total metric gamma grad phi f dot a f? It will be basically the primary gradient, right, with the derivative being replaced with the linear profile assumption, right. So, this will be gamma f times a f dot a f by a f dot E xi times phi 1 minus phi 0, right, and we have a delta xi f. I would like to write it here as phi 1 minus phi 0 by delta xi f, plus we have secondary gradient of f. Fine. So, now do you see what is the coefficient for your a and b? What is the coefficient for your a and b terms? This will be the coefficient, right. Whatever is multiplying phi 1 would be the coefficient for your a and b, right. Essentially, a east phi east is what we have written in a Cartesian orthogonal mesh. Here the neighbor a and b would be this coefficient, right, and the same coefficient will also get added to which one? A 0, a p as well, right, because you have phi 1 and phi 0, both of them having the same coefficient. So, the contribution from a and b will also go to a p, and also there will be one contribution to a and b also for phi and b, right, that we see. Of course, we are not talking anything about SGF as of now. Fine. So, let us say if we have an orthogonal mesh. So, if we have an orthogonal mesh, what would be this quantity that we have, the coefficient, what would this be? This a f dot a f by a f dot E xi. A f dot a f would be how much? A f square, right, this is the magnitude square, divided by what would be a f in the direction of E xi? That will be a f, right, the magnitude. So, essentially this will be a f magnitude. So, this will be eventually how much? Just the magnitude a f. So, what will be the coefficient now for phi a and b? That will be gamma f a f upon delta xi f. Do you see that we have got back our orthogonal coefficient? Let us say if one of the cells or all the cells are of orthogonal in nature, then the formula that we have developed will revert back to the right expression in the context of an orthogonal mesh, right. So, this is gamma f a f by delta xi f. This is also in line with the Cartesian values that we have developed before, right. How much was the Cartesian thing? That was gamma f delta y upon delta x e, right. Do you see that the correspondence between these two? Okay. So, if we have an orthogonal mesh, the primary coefficient will so, for orthogonal meshes, the primary coefficients or the primary gradient coefficients will revert to the correct expressions, right. Okay. They will revert to the correct expressions, thereby the formulation will be the one which is for an orthogonal mesh. Okay, what about the secondary gradient? The secondary gradient term would go to 0. Okay, so why would it go to 0? Because secondary gradient term is nothing but minus gamma f af dot af by af dot e xi times e xi dot e eta times phi eta f. This would go to 0 because e xi dot e eta would be 0 because they are orthogonal, right. So, essentially this term goes to 0, as a result the secondary gradient term goes to 0 and we get back our orthogonal cell formulation in this particular context. Okay. Questions? Yes. We will revert to the correct expressions, essentially right expressions for an orthogonal mesh, yeah, correct expressions for orthogonal meshes, right. Or the formulae that are derived for orthogonal mesh, okay, would be obtained. Okay. Fine. Okay. Everybody all right with this? Okay. Now, the thing is the calculation of secondary gradient is somewhat problematic. We say this because we do not have data in the eta direction directly available to us, right. For the primary gradient, which is partial phi partial xi, we have the cell centroid values and we could compute it directly. Whereas, for calculating partial phi partial eta, what do we have? We can name this as, let us say, some a or a and b, right. Let us call this as maybe b, right, that is what we are using, b and this vertex as a, right. So, if we want to calculate partial phi partial eta, we somehow have to calculate phi at these vertices, right. We need to calculate what is phi at b and we need to calculate what is phi at a, right. But this data is not directly stored, right, that is not what something is solved for. But how do you calculate phi a and phi b? Using interpolation, right. Essentially, you have several cells, using all the cell centroid values, you can somehow calculate what is phi a and phi b and then use that values to calculate what is partial phi partial eta. Okay. All right. Now, it turns out that is what we can do in the context of two dimensional problems. We will kind of see one by one in under what conditions we can calculate these. Okay. So, let us say if we have a 2D structured mesh. Okay, if we have a 2D structured mesh, that means we are talking about a two dimensional curvilinear mesh, right, which could be probably something like this, right. So, essentially we are talking about a mesh like this, where these are maybe some xi equal constant and these are eta equals constant lines, right. These will define our cells. This is some kind of a curvilinear coordinates and these are our C0, C1 or east and west and so on, and we are interested in calculating what is the gradient on this face in this direction, right, that is our eta direction, right. Or let me write this as xi equal constant, this may not be, let me change this thing. So, this is xi equals constant, let us call this as eta equals constant. Okay. So, that is what we have, and then what would be the gradient in this direction. So, we want to have, we will call this as b, this we will call it as a, right, and then using these cell centroid values, we can calculate the value of phi b, right. Similarly, using all these cell centroid values, we can calculate the value of phi a, right. Essentially, phi b and phi a can be calculated, right, using all the cell centered values by using interpolation. And of course, partial phi, partial eta on the particular phase f, right, which is an expression inside the secondary gradient, can be calculated from phi b and phi a values, right, essentially as phi b minus phi a upon delta eta, right, on that particular phase, right, it can be calculated. Of course, you do not have to calculate it this way, you can also calculate what is the gradient at the cell centroids itself, right. Instead of interpolating phi, you can calculate what is partial phi, partial eta at cell centroid C0, and you can also calculate what is partial phi, partial eta at cell centroid C1, and then interpolate these two to obtain what is partial phi, partial eta on the particular phase f that is shared between these two cell centroids, right. That can also be done, right. Either you calculate the dependent variable at a and b and calculate the gradient, or you directly calculate the gradient at the cell centroids and then interpolate them onto the face. You see that? Either of the methods can be used, okay, and we can certainly calculate this. Or is it possible to calculate the same way if we have an unstructured two-dimensional mesh? Yes. They should give the same answer if your interpolations are. If you use harmonic interpolation, okay, they should actually give the same answer, right, for the second method, right, then it should give the same answer, right. So, these two methods, either you calculate it this way or you calculate it this way, would they give the same answer? That is the question. They should give the same answer, right, as long as your methods are correct. The interpolation methods are the same, it will give you the same answer, okay. Now, what will happen in the context of a two-dimensional unstructured mesh? Can we calculate it in a similar way? We are talking about a 2D unstructured mesh. So, okay, the question is, how do I calculate this quantity at the cell centroid, right? How do I calculate partial phi, partial eta at C naught? How do you calculate it? You would need essentially you would need the north and the south values here, right. So, one way is to basically calculate partial phi, partial eta here and then average them, right, or use some kind of interpolation. So, on the north face you would use, let me number these things, okay. This is 1, this is 2, 3, 4 and 5, okay. So, essentially you would calculate partial phi, partial eta on the north face, right, which is coming from C0 and 3, right, and similarly you would calculate in the south face. So, partial phi, partial eta on the south face you will calculate from whom? C0 and cell 4, right, and then interpolate them, right. Essentially you got it on the faces and then you can interpolate. That is one way. Of course, you can also use directly the 3 and 4 values and then calculate also, right. So, it depends on the order of accuracy of the method that you are using, okay. There is no single way to do this, right. You can also have a bigger stencil and then include more cells as well, right. Any other questions? So, there are essentially several methods. We are not going into how exactly do I calculate, but given the cell values we can calculate these things, right. Okay. That is clear? Fine. Any more questions on this part? Partial phi, partial eta? No? Okay, that is good. Then what about if we have a 2D unstructured mesh? Can we use a similar strategy to calculate the partial phi, partial eta or not? If we have a 2D unstructured mesh, that means let us say we have triangular cells, right, which we have started off with. So, essentially we have some triangular mesh, okay. So, can I do a similar strategy? So, we have C0 and C1, we call this as B, we call this as A. Can we Of course, the interpolation method has to be now generic enough such that it can interpolate for this unstructured mesh, right. But somehow if let us say we know how to interpolate on this unstructured mesh, can we apply a similar strategy? Right. We can calculate what is phi b, we can calculate what is phi a, and then calculate what is partial phi partial eta, right. That is basically in this direction. I can calculate partial phi partial eta on this particular phase from phi b minus phi a upon delta eta, right. Can I do that? Essentially obtain interpolate to get phi a and phi b, and thereafter apply this formula and then calculate what is partial phi partial eta, right. How do I interpolate is the question. So, I have cell values stored at here. Let us say I am talking about phi b, then I have these cell values. I somehow have a generic 2-dimensional interpolator which will interpolate these and calculate what is phi b, right. It need not be symmetric, it depends on the whatever is the delta r bar that you have with this, and then you would have another delta r bar and so on, right. From there you can calculate, okay, fine. So, in principle this can be obtained, right? And then we can certainly calculate what is partial phi partial eta and then move on with the calculation, right. Any questions? Okay. Oh, feels fine. What is the unknown we are trying to solve? Phi, but what are we trying to calculate here? Gradients of phi. Phi itself is not known, right. We are trying to calculate gradients of phi and then we are happy with it, right. We are calculating, but what is the catch here? How are we calculating gradients of phi? Using which values? Using previous iteration values. That means these are all what? Star values. These are all the provisional values. Now, when you put in a star value there, will this go into the coefficient matrix on the left hand side? A. You have let us say A phi equal to B. Where will these terms go? These contributions? They should all go to the right hand side B, right? They will all go to the B term. Okay, that is what I wanted to draw your attention. So, only the coefficients that are arising out of the primary gradient will go into the coefficient matrix AP, A neighbors, and all these guys will go into the right hand side vector, right. All the secondary gradient stuff SG sub F will all go to the right hand side. Okay. Now, at the time of convergence what would happen? Phi b would be same as phi b star and your secondary gradient would be obtained exactly. It will not be 0, it will be obtained exactly, right, that is all, correct. Okay. Fine. Questions? No? Clear. Okay. Let us move on. Then we have finished a 2D structured, 2D unstructured. What about a 3D structured mesh? Yes. Yeah. Okay. So, the question is can't I put in the secondary gradient also into the coefficient matrix, right. So, the thing is you are calculating phi b from phi neighbors, right. So, can't I add all of these guys into the coefficient matrix A? You can do that, but what would happen? What will happen to the matrix? Diagonal dominance, it will not be banded. Diagonal dominance is one thing, it will not be diagonally dominant. We will see why it will not be diagonally dominant. What is the other one? The bandedness is not anymore valid, right. It is kind of, we are in an unstructured thing, but still your coefficient matrix will have several terms, right, because now up till now only the face neighbors are will enter the coefficient matrix, right. For example, if you have a triangle for corresponding to 3 faces, you will have 3 cells, but here the vertex neighbors also will enter the calculations, right. The sparsity of course will be affected, and then another issue is that the diagonal dominance would also get affected, because the interpolation need not yield a kind of a diagonally dominant system. Okay, we will see that. So, one of the ways you can do this is preserve your matrix structure A that is only depends on the face neighbors, and then put all of these guys into the right hand side. Okay, that is the strategy we are following. but nonetheless you can also do it that way, the other way, okay. That is also possible, but for the purpose of this course and for the purpose of all the software that you will be using, let us say all the open source and commercial software, this is how it will be treated, right. All the secondary gradients would be put into the right hand side to improve the properties of the matrix, okay, the diagonal dominance and maintain the structure of the matrix, okay, which will be only connected to the face neighbors, not to the vertex neighbors. Other questions? No? Yeah. Yeah. So the question is, if I want to use an implicit method, right? I have an implicit method. I have to use all the current values, right? In that context, what shall I do? We can't do this. What will you do if you have an implicit method for source terms? You have an outer loop and an inner loop, right? You have already linearized the source term, right? You have SC and SP phi P. Would you use your SP is anyway going there. What would have used for SC? Have you used the previous values, right? So you use the current iterate values, right? So as far as the implicit method is concerned, these secondary gradient terms would be still treated as previous values, the current iterate values, okay? We can do that. It's just that the coefficient matrix will become really dense, right, and some of the properties may not be satisfied, which we will see, right. Essentially, by doing this kind of a trick of dumping all the secondary gradients onto the right hand side, we are changing what? The path to the solution, right. We are changing the path to the solution, not the solution, right. The final answer will remain the same when you achieve convergence. We are only changing the path to the solution. So we could of course do it the other way by including all of these things, but the only thing is the matrix may not be conditioned. As a result, we may not obtain a solution in the right way, okay. Other questions? No? Okay, let's move on then. So what about, we have finished 2D structured and 2D unstructured. What about 3D? Let's start off with 3D structured, okay. We have a 3D structured mesh. So that means we have some kind of a quadrilateral, okay. We are talking about a structured mesh. So let me put in some kind of a quadrilateral mesh here, or sorry, 3-dimensional, so cuboid kind of cells, right. So that's what we have. This is 3 dimensions, and then we have of course the cell centroid, and this is connecting the other cell centroid, which is here, right, and this we call it as some xi equals constant, right, that is along the cell centroids, right. And up till now we have only eta, which is along the face, right. But now what is the face right now? This is the face, right. This is the face we are talking about, and how many, up till now we had only eta in this direction, right. Now we have 2 directions, right, on the face, which is eta along this direction and some zeta along this direction. So we have essentially eta, and then we have some zeta, right. So we have these 2, that is along the plane, right. On the plane we have 2 directions, and then normal to the plane we have xi, which is connecting the cell centroids. Do you see that? Okay. So we have xi. Xi is perpendicular to the plane at that location. Would it be always perpendicular? Need not be, right. Okay. Fine. So that means up till now we had only A and B coordinates. Right now we will have 4 more coordinates, right. We will call it as A, B, C, D. These are the 4 vertices, right, where these eta and xi needs to be calculated, right. So that means if we were to write this value gamma grad phi dot AF on a 3D structured mesh, right, what will be the gradients look like? You will have 3 terms, partial phi, partial xi f, partial phi partial eta f. We will also have partial phi partial zeta f, right. In the 2D we only had 2 terms. In 3D you will have these 3 terms. Do you see that? Yes or no? If you go back for 2D we had only this is the primary direction, right. We had the primary direction, and then because this is not orthogonal you have these 2, right. Your E xi dot E eta is non-zero. Similarly, you will have E xi dot E zeta also non-zero, right. As a result you will get 2 secondary terms. Do you see that? If we just redo the entire thing what we have done for 3D, you will see that there will be 3 gradient terms, right. If you were to boil it down, let us say to a Cartesian 3D mesh, you essentially have these corresponding to these 3, you have partial phi partial x, partial phi partial y, partial phi partial z, but then because Ax is only pointing in the I direction, the partial phi partial y and partial phi partial z terms would go to 0, right. You had only one phi 1 minus phi east minus phi p by delta x surviving, right. In the context of non-orthogonal meshes, all these 3 will survive, right. We are talking about a 3D structured but non-orthogonal, okay. Fine. We are not saying how will we generate this thing, but somehow let us say we end up having a 3D structured and non-orthogonal mesh, then all these things will survive, right.
Sir, it can also be a combination of orthogonal and non-orthogonal.
It can be. We are talking about a particular cell, right. Anyway, if you have some orthogonal cells, our formulation will revert to an orthogonal formulation anyway, right. So, we are developing everything for non-orthogonal in this present context, okay. Okay, we have these 3. So, when we say secondary, so we know how to calculate this guy, right. How do we do this thing? Same as before, right. This will be phi 1 minus phi 0 by delta xi, that means this is C1, this is C0, right. So, this distance would be your delta xi, and then you will, and these coefficients will go into the coefficient matrix, right. What about these 2 terms, partial phi partial eta, how can you calculate? Now, you somehow have to interpolate it to the vertices A, B, C, D, right, these 4 vertices A, B, C, D, right. Once you have values there, can you calculate A, B, phi A, partial phi partial eta? You can calculate from A and B. Similarly, can you calculate partial phi partial zeta? You can calculate, right, from the values of phi A, phi B, phi C and phi D. We can obtain these 2 secondary gradients, right. So, just like the way we have done in the context of 2D, we can do this in the context of 3D also, okay. Fine, any questions? So, these are all again starred values, the existing values of phi we are using to calculate gradients on the faces in the 2 other directions other than the line connecting the cell centroids, other than the primary direction, right. Okay. This can be done. All right. Okay. Fine. So far so good. We have devised different ways of calculating the secondary gradients. Now, what will happen if you have a 3D unstructured mesh? If you have a 3-dimensional unstructured mesh, that is of course also non-orthogonal, okay. So, if we have an unstructured mesh, how does your cells look like? Let me kind of take a tetrahedron, okay. So, let me take a tetrahedron. So, this is basically tetrahedra. So, this is what I have. So, we have the cell centroid somewhere here, let us call this as C0. This is connecting to another cell centroid, that is C1, right, that is what we have. Now, we are talking about one particular phase, that phase happens to be this guy, right. That is the phase we are talking about, which I have highlighted. Let us say this is the phase we are talking about, right, out of the tetrahedra. Now, can you calculate partial phi, the secondary gradients in this context? There are 3 sides. So, are there, can you, so essentially what we have to do is, if we call this as some xi direction, right, we would end up having two different directions, right, which is basically if you are calling it as xi eta and zeta, this is our primary direction, these are our secondary directions, right. Now, are eta and zeta coming because we have assumed some kind of a structure? No, right, that is not the case. They are coming out because we have 3 axes, right, we are doing a 3D, right, that is why they are coming out. So, essentially we again will get these gradients, which is partial phi partial eta on this particular face, and we will also get partial phi partial zeta on the particular face, which we have to calculate, right. Up till now we could easily calculate them because either the eta direction is aligned with the phase direction, right, we could calculate what is A, B and calculate them in the context of 2D. Similarly, in the context of 3D, when we have a structured mesh, we could identify the phase by kind of splitting it along the 2 sides, and we said A, B, C, D, there are 4 points, we can interpolate and calculate. Now, we have to actually take 2 directions here, right, and the 2 directions, where should they lie? They should lie in the plane of the face, right. On the triangular face, you need to identify 2 directions. Do these 2 have to be orthogonal? No, they do not have to be orthogonal. There are 2 directions. That means you can pick infinitely many directions, right, on this plane, right. There are many that are arbitrarily available, can be picked arbitrarily, but of course you can also come up with one particular way of choosing them, right. Essentially, we want one way consistently to pick this, but we are flooded with infinite options, right. We have to pick one such that we can code it, right, that we can write a program. Now, what is the another complexity that comes in here? Right now, I have drawn a tetrahedra which has 3 sides on the face, right, but in general, if you have an unstructured mesh, this can be an n-sided polygon, right. This can be an n-sided polygon, this face can be an n-sided polygon, right. That means, for that particular n-sided polygon, we have to pick 2 directions which are eta and zeta, right. Now, that we cannot have a consistent way of picking something, okay. That means, there are infinitely many possibilities, out of which we have to pick one set of eta and zeta. Now, we may devise something only for tetrahedral meshes. For example, you can say, okay, why not I connect this vertex with this direction and this with some other direction here. Can I pick this way? Yes, you can pick, right. I can connect. Of course, you have another third direction that you somehow come up with some consistency, okay. So, the idea is, but this will not work if you have let us say a pentagonal face, right, or an octagonal face, isn't it. Let us say if you have a polyhedral cells, something like a honeycomb structure, you can have many, you can have basically the face need not, it will be an n-sided polygon in general, right. In that context, how do you choose these 2 different directions? That is the question. So, that means what we are convinced is that in the context of 3D unstructured, there is a problem. The problem is there are infinitely many ways you can pick the eta and zeta, right. Eta and zeta can be picked in infinitely many ways, but what we are looking for is we want to look for in a unique way by which we can implement this for all the cells, irrespective of whether we get a tetrahedron or we get a hexahedron or a prism and so on, right. For example, if you got a prism, 3 of them have the triangles, the other one has a quadrilateral, right, then this would not work. So, as a result, we need to have a particular unique way of calculating the secondary gradients such that it will work for any shape of the cell, right, any shape of the cell, okay. So, we will look at one particular way, which is again available in most of the commercial and the open source software, in any of these CFD software, that is what we will look at, but you are welcome to use any other method other than this thing, okay. But as far as the course is concerned, we will follow this particular method in terms of the problem solving and on, okay, and so on, or if you end up writing a program for calculating these things for your project, okay. So, Is the problem clear what we encountered? Yeah. Okay, so in the structured case, how did we choose the two directions? So in the structured case, I have a face, right? I can choose maybe the midpoint of this line, right? And then essentially I have chosen the midpoints here, 1, 2, 3, 4, right? I just need to choose two different directions on this particular plane. I chose it to be passing along the center of this rectangle or quadrilateral. Here it is. So essentially, if it is a multi-sided, then you cannot do it this way. So implicitly, what I have is when I say structured, we are talking about a hexahedral mesh. Okay, because you would not be able to generate a tetrahedral mesh that will be structured. That's what I assumed. Okay, so we are talking about a bricks kind of thing, like a quadrilateral mesh, a hexahedral mesh, and where all the faces are quadrilaterals. Right, then you can somehow define two different directions, right, connecting the midpoints of the edges, right, that can be done. That's what we have targeted. But certainly whatever we develop now for the 3D unstructured meshes should also work for the 3D structured meshes, right, when you boil it down. Because you may have several tetrahedra, all of a sudden you may have some prisms, and these prisms might be connected to some hexahedra afterwards. Let's say if we have a kind of a mixed cell shapes. Right. Other questions? Is the problem clear? Okay. So there are infinitely many ways you can define this and calculate, but we will look at one particular way. That way is basically is what is used prominently. So this is basically calculation of secondary gradient. Okay, calculation of secondary gradient. Now, here is where you have to be a little focused. So, what is the expression we have? We started off with calculating what is gamma grad phi f dot a f, right. This is what we set off calculating, and we have written this as gamma f by delta xi f times a f dot a f by a f dot xi times phi 1 minus phi 0 plus secondary gradient of f, right. That is what we have written, is not it? That is what we have written. Now, what is the expression for secondary gradient? Secondary gradient for f is given as minus gamma f times a f dot a f by a f dot xi times xi dot e eta times partial phi partial eta on the face f, right. This is what we got, is not it? Let us say I am talking about 2D, this is what I got. If it is 3D, you would have one more term, might be there. Now, the idea is to calculate the secondary gradient from the already calculated primary gradient value and the total value. Okay. So, the secondary gradient value should be nothing but the total minus the primary gradient value. Of course, the thing is we do not know the total gradient. If we knew that, the problem would have been solved, right. So, now we are looks like we are going in circles, but we will come to one point. So, essentially calculate the secondary gradient, which is the minus of this thing, as the total minus the primary gradient, because the primary gradient is always uniquely defined, right. The C0 and C1 are always uniquely defined, xi is always uniquely defined. So, I can definitely calculate what is that for any cells that are given, right. So, that means this secondary gradient of f can be written as what is gamma f grad phi f dot a f, right, that is the total value I have, right, minus I would subtract off the primary gradient. Okay. The primary gradient is how much? Is this guy, right. I would subtract that off. That means minus gamma f by delta xi f a f dot a f by a f dot xi times grad phi f dot xi times delta xi, right. Do you agree with this? So, what I have written is I have changed a little bit here. Okay. Instead of writing phi 1 minus phi 0, I have replaced that with the grad phi, right. I somehow know what is the gradient on the particular face. Okay. So, I know that. So, that if I take a dot product with the xi direction, I would get the component of that in the direction of xi, multiply with delta xi, that will give me what is this difference phi 1 minus phi 0, right. Do you see that? I have replaced phi 1 minus phi 0 with grad phi f dot xi, right. Basically, this would give me the gradient in the direction of xi, that is the primary gradient, times delta xi, right. That will basically give me phi 1 minus phi 0. Okay. Now, what is the unknown in this equation? Of course, secondary gradient itself is unknown, but I have written something here. What is that is unknown here? Grad phi f, right, which I have written here. This particular term here is the unknown. That means, we are calculating gradient of phi on the face which is shared between C0 and C1 somehow, right. So, we are calculating the total gradient on the particular face, and then from there I can calculate what is the total gradient of the diffusion flux minus this is what the primary, right. So, this is the total, this is the primary, that would give me what is the secondary value. Do you see that? Now, we have transformed the problem from the computation of secondary gradient to the computation of grad phi on the face f, right. That means, if I can calculate what is grad phi on the particular face which is shared between C0 and C1, then I can calculate my secondary gradient, right. So, we have just transformed the problem of calculation of secondary gradient into calculation of gradient of phi on the particular face. Have you used any of these software, the CFD software? It would ask you what is the gradient calculation scheme, right, or some kind of how should I calculate gradient, that is what it will ask you, right. This is where, this is what is asking, right. Essentially, grad phi is, this is what it is asking about, which scheme shall I use to calculate this, and why does it have to calculate this? For use in secondary gradients, that is one reason, but it is also used in many other many other contexts, okay, which we will see in what other contexts you would need the grad phis. As of now, it is for the calculation of secondary gradients in case if you have an unstructured non-orthogonal mesh. Now, it is certainly a good idea to make use of this structure and calculate secondary gradients directly from A and B or A, B, C, D values and put it in there, but none of the softwares work that way, because although you have a structure, they will still use this secondary gradient calculations and calculate it this way, okay, calculate it this way is what they do. But in your own codes, if you have a structured mesh for 3D, or if you have a 2D structured or unstructured, it is good to go with the previous methods that we have discussed, okay. But this is the generic way which will work for essentially everything, right. You calculate the total and you subtract of the primary, calculate the secondary gradient, okay. So, this is how all of these commercial ones and the open source ones work, okay, for the calculation of gradient on the particular face f. Of course, again, how do I calculate the grad phi? Usually, grad phi can be taken as average of the cell centroid values. You can take grad phi 0 plus grad phi 1 by 2. That means, you calculate the gradients of phi at the cell centroids itself and store them, and if you want it for the faces, you would linearly interpolate and take it, okay. That is how it works. Now, how this is calculated, we will see in the coming lectures how to calculate the gradients. Now, there is one more question for you. So, let us say we have a linear problem, like the source terms are all linear, okay. We have a constant source term, gamma is also a constant, but we are working on a steady diffusion in 3D with constant source and constant gamma, but our mesh that we have used is non-orthogonal, okay. If we have it like that, what is the modification that you have to bring about, or is there any modification? So, okay, let's put it this way. Let's talk about a 1D problem where you have steady diffusion. Okay, so this is steady diffusion, and you have S equals constant, gamma equals constant. Okay, and then 1D, and we are also looking at a structured mesh, or rather let's talk about orthogonal mesh. How do you solve this thing? Use Gauss-Seidel or something, and then once Gauss-Seidel or Gauss-Seidel, and once Gauss-Seidel converges, you are done, right, because there is no nonlinearity either in gamma or in S anywhere, right. Now, let us say if it is a 3D problem, but it is still orthogonal, how do you solve it? You perform iterations using Gauss-Seidel, right. You start off with some initial guess phi 0, right, phi 0 bar, and then once this phi 0 you perform the iterations, and once you converge phi, are you done with the solution? It's constant source, constant gamma, and you are also working on an orthogonal mesh, right. Now, what will happen if you have the same problem 3D steady diffusion with constant source, constant gamma, but you are working on a non-orthogonal mesh? Is there any change that you would see, or you have to incorporate any other change? Would this work this way? You have a Gauss-Seidel, you perform let us say 10,000 iterations and you converge. Is that the solution that you would obtain, or do you have to make any changes? Sorry, you have a non-orthogonal mesh, but there is no nonlinearity. The source term is constant, gammas are constant. Secondary gradient, yes, who said secondary gradient? Yes. So, because of secondary gradient, what do I have to do? Two loops. It has to introduce an outer loop, right, because the secondary gradients that I have used in the calculations are calculated with a previous value of phi, right. So, as a result, I would need an outer loop, right. This would introduce an outer loop just because my mesh is non-orthogonal, right. If it were not, let us say if it were orthogonal, under what conditions would you get an outer loop? If you have nonlinearity either in the source terms, gamma, or any other nonlinear terms, right. So, that means if your mesh is non-orthogonal, even if you have a linear problem, you still have to go with an outer loop. Okay. That is because of the calculation of the secondary gradients, and we have calculated secondary gradients in what fashion? We have calculated in a deferred fashion, right. We have used the previous values, right. But as somebody suggested, if you were to directly calculate all of these things in the coefficient matrix itself, then you do not need an outer loop, right. Okay. Is that clear what we just discussed? The need for an outer loop if you have deferred way of calculating the secondary gradients. Okay. Okay, think over it. We will come back to this discussion later. All right, I am going to stop here. I will see you guys in the next lecture. Thank you.